Alright, so welcome to Math341, Lecture 15. What we're going to do today is we're going to do the CDF method. After we do the CDF method, we are going to do one of my favorite problems, either the marriage problem or the secretary problem. In previous years, one of my students told me that he was going to use this to choose his spouse. He is still single. There's a difference between theory and practice. I am not encouraging anyone to apply this method to their lives, right? So you've actually had one homework problem related in some sense to the CDF method. And it doesn't look like it was an important homework problem. It looked like it was just another standard problem. There were no bells and whistles or stars around it. It was, if you can generate a uniform random variable and you have a nice CDF with a nice inverse, show that you can generate any random variable with that distribution. Tremendously powerful. And so it means that if you have a uniform random number generator, you can use this to do a lot of things. So what I want to do today is I want to explicitly talk about how, if I give you one random variable, we can pass from this to the distribution of another random variable. So let's say x is uniform on 0, 1. So this means the density function is equal to 1 if 0 less than equal to x less than equal to 1, 0 otherwise. And the cumulative distribution function, well, I just integrate this function. So it's going to be 0 if x is less than equal to 0. Then I'll just get x if 0 less than equal to x less than equal to 1, and then 1 if x is greater than equal to 1. So this will be the CDF of the uniform random variable. And you can just quickly check and see if this is true. And you do see that the derivative of the CDF is the PDF. So here is the CDF, and here's the PDF. Now there are a few places where the derivative might not exist. It's where we have a change in definition. If you notice, the function is continuous. Here it's 0, and then here it's 0, and then here it's 1. But the function won't be differentiable at those 2 points. That's fine. All right, so what we want to do now is we want to look at a new random variable. Let's look at y equals x squared. One of the simplest non-trivial things I can do. I could have shifted my variable x by 5. Well, that's not going to be that difficult to see how this changes the PDF and the CDF. I could have rescaled x by 3. Again, not really going to be that interesting. But squaring it, this introduces something new. So we want to calculate what is the density of this new random variable. So what we'll do is we'll let the cumulative distribution function of y is the probability that big Y is less than equal to little y. Now, what possible values can little y take on? Yes?
From 0 to 1?
Yeah, 0 to 1. Once y is greater than 1, in fact, it's really the same as y equals 1. Right? Because once little y is at least 1, we know the probability is 100%. Because we know this lives in 0, 1. So I will assume 0 less than equal to y less than equal to 1. Because if y is outside that range, if y is less than 0, the probability is just 0. And if y is greater than 1, the probability is just... So I'm going to just do the interesting range. So the probability that big Y is less than equal to little y is the same as the probability that x squared is less than equal to little y. What is the probability that x squared is less than equal to little y? How should I write that? So I don't want things in terms of x squared. I don't know things about x squared. What do I know? I know things about
Square root of the big Y?
Yeah. So this is the same as the probability of what? I want things in terms of x. Yes?
So between minus root Y and root Y?
Yes. You have to be careful. Right? Because x could be negative, and it would still square to something at most y. Now we immediately realize, well, x is never negative, so we can simplify this, but you have to take that step. And now it's just the probability that x is less equal to the square root of y. Well, we actually know explicitly what the CDF is. The CDF is just x. So this is just the cumulative distribution function of x evaluated at the square root of y. It's just the square root of y. So we can now calculate the density function. So the density function is the derivative of the CDF. And now I just take the derivative of square root of y, so I'll have 1/2 y to the negative 1/2. And this will be for 0 less equal to y less equal to 1. Is there anything that makes you uncomfortable? Yes?
Y equals 0.
Yeah, when y equals 0, I'm a little uncomfortable. But that's only at a point. So my uncomfort is minimal. Everywhere else it's fine. And in fact, this function is still integrable. So as a check, to make sure we haven't made a mistake, we can integrate from 0 to 1 of 1/2 y to the minus 1/2 dy. And we'll get 1/2 y to the 1/2 divided by 1/2 at 0 and 1, which equals 1. So even though the function blows up, even though it has a singularity, it's a really weak one. The function is still integrable. To me, this is absolutely amazing. You start off with a function, uniform random variable. That's a nice probability distribution. And you square it. And now all of a sudden you have something that has an infinity in it. This just warns you how careful you need to be with all these calculations. All right. So we can now calculate the probability density function of this absolutely fine. How large can my density be? It could get arbitrarily large at a point. So we had, homework problem, can your probability density be very large? Yes, but only on a very small neighborhood. And the larger it is, the smaller that neighborhood has to be. If your random variable is discrete, how large can a discrete random variable be in probability? Yeah, it can't be more than, it's at most 1. But for a continuous random variable, the density function can be extremely large on extremely small swaths. So this is the CDF method. I applied it for x as a uniform. Another good example is let's let x be normal 0, 1. So this means the density function of x is 1 over the square root of 2 pi e to the negative x squared over 2. As a nice exercise, let's let y equal x squared. So for those of you who have taken stats, what distribution is y? Anybody remember? Be more specific. There are infinitely many chi-squared distributions. Which chi-squared distribution it is? You're close. You have to tell me the degrees of freedom. How many degrees of freedom does this chi-squared have? 1. So this is a chi-square with 1 degree of freedom. For those of you who have not done statistics and not seen chi-square distributions, do not worry. We will do a lot with them later. And for those of you who want to make sure we do pure mathematics, we will use this to calculate the volume of the ball in the n-dimensional space. All right. It's a nice application of chi-squared random variables. All right. Any questions on the CDF method? All right. So we're going to now turn to the main part of today's lecture, the marriage problem or the secretary problem. We will make some unreasonable assumptions. All right? Well, we'll start off with some reasonable assumptions. We will assume that you are interviewing somebody either for a job or for marriage, and you are so desirable based on who you are, where you go to school, that people cannot imagine life without working for you or being married to you. And if you decline to have them, they will kill themselves, because life is just not worth living. This gives no chance of hooking up with somebody later in life, no chance of a relapse, no chance of changing your mind. There are consequences to actions. If you say no, it is a permanent no. Right? Is this reasonable? For most of us, probably not. Now, what will often happen is if you say no to somebody, what might happen? What might that person then do?
Kill himself. Spread the word.
Spread the word. So let's say you're interviewing for a job and the company doesn't give you the job. And for those of you who are seniors, this may be happening. What do you do if a company doesn't give you a job? If anybody thinks the answer is kill yourself, please talk to me. What do you do if the company doesn't give you a job? Move on to another company. Try another company. Right? And so a lot of times what will happen in the real world is you might decide later on, damn, that person was the best candidate. And by that point in time, it's too late. They've already been taken up by someone else. Sometimes they might still be available. They might decide, I had a friend who was working at a big firm in Boston, decided if he'd made enough money, he always wanted to be a chef, and asked me to write a letter of recommendation for him to get into chef school. I said, I'd love to do this. I could talk about your preparation in liberal arts and working with you. Sure. It was a very fun letter to write. He lasted 2 days. He couldn't deal with how stupid a lot of things were at that place. And then he went back to the firm that said, whenever you want to come back, you're always welcome back. So in real life, you can always, or at least you can often have the possibility of changing your mind or getting people to come back later. We will do a simplified assumption that once you say no, the candidate is no longer available. Do you want to do this as marriage, or do you want to do this as hiring a secretary? First loud voice wins. Marriage. Oh, okay, it's a tie. I need next loud voice.
You want marriage?
I had marriage.
Oh, good.
And again, one of my students who is single is still trying to apply this. So you will see people one at a time. And all you can do is you can evaluate their relative value to you. So you're not going to give absolute numbers. You'll say, this is better than this person, this is better than this person. And you want to choose the best possible person. If you end up with the best possible person, it is considered a success. If you end up with the second best or the worst, it is an equal failure. Okay, is this reasonable? No. There is a huge difference between ending up with the second best person and the absolute worst person. For this analysis of this problem, however, we will consider those two outcomes equally bad. That if you do not have the best, it just doesn't matter. Anybody ever watch Mad TV? Years ago, they had a set of routines called lowered expectations for people who had been dating unsuccessfully for many years. So what do you think will happen in real life if you have not found a spouse as you get older and older and older? Maybe we shouldn't say anything out loud. It's not necessarily a romantic way to propose to someone and say, I think we should cut our losses and get married now. But at some point, you start to get afraid of ending up with somebody really bad. So in terms of marriage or in terms of hiring somebody for a job, at some point you might say, this person is good enough. It's probably not the best, but I want to minimize my risk of getting the absolute worst or getting somebody very badly. I'm willing to settle at this point. We will assume the following. Assume there will be n candidates. And we will assume that you actually know how many candidates there are. One of my favorite undergraduates, I actually emailed him recently because he's a Yankee fan. He did this problem where you assume that n is unknown and is drawn from different distributions. And how does that affect your strategy when now you don't know how many candidates you will see? Do you know what day he gave his colloquium on this? Yes, has to be Valentine's Day when I'm asking something like this. It was one of the best Valentine's Day colloquium I've ever seen at Williams. Yes?
How is your student applying this if he doesn't know how many candidates there are?
You have to generalize your argument to deal with the fact that now n is a random variable. And what should you? I'm sorry. Yes. I mean, this has been done before, but you can do it for different distributions, and you can try to come up with what's the optimal strategy, what's the optimal chance of success. So, win if have best, lose otherwise. So there is no margin for failure, and there's no shades of losing. If you do not have the best, doesn't matter if you have the second best or if you have the worst. Later on, you can, of course, remove that assumption and say, what strategy might give me one of the top 2 or something like that. So if decline someone now unavailable. So can somebody give me a strategy where you will have the best person 1 over n of the time? Yes?
Pick the first person.
Good. Can somebody give me another strategy where you will get the best person 1 over n of the time?
Pick a random.
Pick a random. So we will assume people randomly ordered. I'll put uniform. So if you just pick any number, I will always take the 17th person because 17 is my lucky number. All of these strategies will win 1 over n times. So it can win 1 over n if always choose a fixed spot. Something similar to this happened years ago with the US with, I think, the green card lottery. It was supposed to be a random process as to who gets green cards, but it turns out that they only randomly chose from people who applied in the first 2 days of the period. And there was then a court case as to, does this count as a random method? It was random but not uniform. I will try to find that article and send that along. So this is a strategy. As n gets larger and larger and larger, how comfortable do you feel with this strategy? Not so good. So the question is, do you think you can come up with a strategy that will win 100% of the time? Yes?
Have n equal 1.
N is getting large, but nice. Okay. If you know n equals 1, absolutely you will be fine. But in general, you will have some large n, and imagine n is going to infinity. What is your best strategy as n goes to infinity? Does anybody think you can be right 100% of the time? Now what's interesting, yes?
Well, can you assign anyone with a score of 100 since everything is relative?
Well, but it doesn't matter what scores you assign people. All that matters is, are they better or worse than other candidates? I just want to end up with the best person. I don't really care about what their numerical value is.
Well, if the scale is 1 to 100 and the second person is a 100, their PhD.
Well, but you don't know that their scores go from 1 to 100.
Okay.
All you can do is when you see a person, you can then compare them to other people you've seen. This is why I often do this with the envelope problem and do the envelope problem first. I'm not doing the envelope problem now. We don't know the distribution of their value.
So there's no way to give someone.
There's no way to give somebody a numerical number and know, I've just gotten the 100 or just gotten the 10. It's possible to get 100% without always being right. So for instance, if you are right n minus square root of n over n of the time, and the limit as n goes to infinity, that would actually be 100%.
Can you accept someone and see someone else?
Nope. Once you accept somebody, you've accepted them. You're done.
So you can't compare them to the next person.
Nope.
And choose for them.
Nope. You see somebody and you either take them or not, and if you don't take them, they kill themselves. They are this is why I'm being violent. I need to really drive home to you opportunity cost. If you say no, it's gone.
So we pick the first person, that's a 1 over n.
Correct.
So we're assuming we can do better than that. So I assume we don't pick the first person. If it's a matter of comparison, maybe we could say that, assuming that they're in a certain rank compared to everyone else, after we get to X amount of people, we
Okay.
account for how many people are better than the others.
So imagine, here's our people.
Where at a certain point, it's
Well,
where at a certain point you would say it's unlikely that there's someone better than this based on how many people have.
Okay, so what you're saying is, as a strategy, we'll look at maybe the first k, and then we'll take first person better than best we have seen. So this is a strategy. If I take k equals n minus 1, then means I always take the last person. If I take k equals 1, I take the first person better than the first person. No matter what the strategy is, what's one of the dangers of the strategy? Yeah, so if one of the best pupils in the first K, you automatically lose. So whenever you do problems like this, you want to be thinking, what are the competing influences? The larger K is, the more chance you have of losing. So you want to keep K small. So as K increases, higher chance you lose for reason of best in the first K. So that is a reason why you would want K small. Why might you want K to be large?
K is small, but you might not have seen anyone great in the first K, and then you're not going to get the best person that thinks
Yeah. As K increases, better chance of getting best. So the more people you see, the better chance you have of getting a good sense of what the market is and then making a good decision later on. But it costs you. And so the hope is that there is some K which is going to be large enough that you will have a good chance of getting the best person, but small enough that you don't have too much of a chance of just automatically losing because the best person is now unavailable. So when you see a problem like this, do you think you can get 1 over square root of n? That's significantly better than 1 over n, but in the limit, what does 1 over square root of n go to? It goes to 0%. Do you think you can get as high as maybe log n over n? That's much less than 1 over square root of n. Do you think you can get a positive percent of the time? Do you think you can get over 30% of the time that you'll find the best person? It seems quite surprising that you would be able to get the best person over 30% of the time, because the more people you look at, the more trouble it is. Yes?
Does this mean the first person is screwed always, given like it's a relative argument? Like you need one?
So in something like this, the first person will never be chosen. So for certain things, you don't necessarily want to be first. Yes?
So we know that when we see someone, we have no idea what the relative distribution of the rest of them is.
Correct.
Like there's no this one.
There is no knowledge.
So it's just like a bunch of random numbers.
Correct. Correct. So you have no, and again, in the real world, you might have some information. You might have some idea of your candidate pool, and then that will absolutely help you with making decisions. So let's analyze the probability of a win. So the probability that we win, and I'll put a K there to remind myself that we are choosing to look at the first K and then doing the best person afterwards. So what percent of the time do we always lose? Yes.
K over n.
We always use K over n. So let best person be at position m. You lose if m is less than or equal to k. You can win if m is greater than k. So the probability that we win is going to be the sum, n goes from k plus 1 to n, of the probability we win given best at m times the probability best at m. We've seen this many, many times before. We're partitioning, right? If we're going to win, we can win with either the best person at k plus 1 or at k plus 2 or at k plus 3 all the way up to n. These are independent events. The best person can't be at both plots 17 and 35. And this is just conditional probability. Yes?
What about the probability that, like, there's some, like, k plus something that is less than m, but like...
Well, so we haven't calculated what these probabilities are yet. So what you're saying is about to come into play.
Okay.
Right now I'm just saying the probability that we win is the probability we win and the best is at m times the probability the best is at m. And now we have to calculate what each one of these are. That's going to be hard, and that's going to use what you're about to say. what's the probability that the best person is at M?
1 over n.
Yes, it's 1 over n. So it's going to be 1 over n times the sum, n goes from k plus 1 to n, of probability we win, given the best at M. So we now have to calculate what's the probability of winning when the best is at M. All right, so let's look at what's going on. Here's the first person, here's the kth person, here's the k plus 1, here's the mth, here's the n. So we're assuming the best person is not in the first k. So do we have a chance of winning? We have at least a chance. What's the only way we lose? What must be true for us to lose?
Like the best person is behind. That's not come up yet.
I'm sorry?
Like the best person is behind the person we choose.
What do you mean by the best person? So here we've looked at the first k, and we're assuming the best person is at M, which is beyond k.
We only lose if there's something between K and M that's better than everything in K but less than M.
Right. So we need the best person in here to beat the best person before here. Right? So of the first n minus 1 people, best must be in the first K.
Professor Miller.
Yes.
Your iPad's having a spasm.
Oh, wow. Okay.
She's going up and down.
Thank you. It just really gets into this problem. So the only way we lose is, imagine the second best person is before M. So they're not in the first K. So we would see that second best person going, they're better than the first K, let's take them. If the second best person is in the first K, we win. If the second best is in the first K, we always win. So actually that's pretty good for us. So that actually tells you might want K to be large, because if the second best person is in and the first isn't, we win. What would it mean for us to lose? Yes?
Because we're assuming everything's randomly distributed.
Yes.
Is the probability the second best is in K, but the first isn't? Is that 1/2? Or
Well, it's going to depend on the lengths of the segments. And again, that's only one way for things to happen. Maybe the second best person is beyond M. But what we know is for this particular version, all we need to do is make sure that everybody from K plus 1 to M minus 1 is worse than the best we've seen in the first K. As long as they're worse, we won't take them. And then we know we'll take M. So we need the best person of the first M minus 1 to be in the first K. What's that probability? So what's the probability that the best of the first M minus 1 is in the first K? What do you think? Yeah, K over M minus 1. Because each of these spots is equally likely. I have to choose one number from 1 to M minus 1. If I choose one of the K numbers to put the best of the first M minus 1 people, I win. So the probability is equal to K over M minus 1. So we get that this is equal to 1 over N. The sum, N goes from K plus 1 to N of K over M minus 1. All right, so this is just K over N. And then it's the sum, N goes from K plus 1 to N of 1 over M minus 1. Okay? And now it's just down to algebra. And the question is, can we get a nice closed form expression for this? So I have deliberately not looked at the algebra because the algebra is not an enormous amount of fun and I didn't want to do it twice in a day. So watch and make sure I don't make any mistakes. So I will need a result from calculus. The sum, n goes from K plus 1 to N. That should look familiar to you. What kind of sequence is that? Where you're summing reciprocals of consecutive numbers.
geometry.
Not geometric. Geometric would be powers, 1, 1/2, 1/4, 1/8, 1/16. So if I give you 1 plus a half plus a third plus a fourth plus a fifth plus a sixth,
Harmonic.
it's harmonic. So I have k over n, and then I'm going to write it as the sum m goes from 1 to n of 1 over m minus the sum m goes from 1 to k of 1 over m. Because now when I do that, it's just going to be the sum from k plus 1 to n. And I'm going to use 1 plus a half plus 1 over n is approximately log of n. Anybody remember the next term? Is it plus or is it minus? Plus. So the next term is plus the Euler gamma constant, and then the next term after that is like a 1 over n. Fortunately for us, all that really matters is the main term. It doesn't even matter if it's plus or minus, because I'm going to then take this and then I'm going to subtract this, and so I'll get this is approximately k over n, and this will be the log of n minus the log of k. And this should be called the birthday problem that we did earlier in the class, in the semester, where we were just trying to approximate how many people we needed. And we got that the number of days, the number of people you needed before you had a 50% chance was like square root of the number of days. It was like square root of n log 4, I think. We want you to just get a sense, and we just did some approximations. So here, I can approximate these sums like this, and when n is large, this is going to be pretty good. K is going to be growing with n. K is not going to be small. All right, what's the log of n minus the log of k?
N over k.
The log of n over k. So this is equal to k over n, the log of n over k. Or this is equal to the log of n over k divided by n over k. So I can view this as a function, f of x is the log of x over x. What do I want to do? I want to maximize this. And so what I'm going to do is I'm going to try to find what ratio of n over k is going to be best. All right? So maximized f of x equals log x over x. Well, let's look at extreme cases, right? How do you find maxima and minima? Okay. All right, so tell me, have I done this problem yet in this class? All right, tell me, I'll do it this way, where my speed is largest. Okay? Okay. Oh, good. The camera didn't turn. Excellent. Now it turns. It'll be interesting as to what's going on in that class over there. All right. So you made a mistake a few moments ago when you said look for where the derivative is largest. I am hoping by doing this, fortunately I don't need my left foot today, that this will drive home the message and you will never, ever, ever make this mistake again. What was the mistake? I still have my right foot, but I'd like to keep at least one foot healthy today. You have boundary solutions. It's not enough to check critical points. It's a good start. Please, always remember check endpoints. Never, ever forget this again. Extreme cases. If you remember the marble problem, you had to check the endpoints. You had a derivative that was always increasing. It means you flow to the end. Okay? Now, if we look at the extreme points here, it's clearly not going to matter. When I take k equals n, I've got the log of 1, which is 0. And if I take k equals 1, then I've got a 1 over n times the log of n. Well, actually, that's an improvement. So even just looking at the first person and taking the best person after the first person is an improvement by a significant amount. So endpoints won't win. They're going to be much less than what we get when we take the derivative. So we get f prime of x, we get to use the quotient rule, right? So the derivative of log of x is 1 over x times x minus, then I've got log of x times 1 over x squared. So f prime of x equals 0 means 1 minus the log of x equals 0 means x equals e. Well, x is equal to n over k, therefore n over k equals e. Is this right? Yes. So k is equal to n divided by e. Good. This is less than n, right? You should not be looking at more candidates than there are candidates. And let's calculate what's the probability of winning. F of n over e. I'm sorry. We're assuming n over k is e. So we get f of e, which is going to be the log of e divided by e, which is 1 over e, which is about, I think, 36.79%. So to me, this is one of the most absolutely amazing results in this subject. That you have greater than a 1/3 chance of ending up with the best candidate, irregardless of how large n is. This is beyond shocking to me. And this is a complete failure is ending up with the second best candidate. That is viewed as equally bad as ending up with the worst candidate. And you still have a 36.79% chance. So you can think of all sorts of additional questions you could ask, and your probability of having any reasonable measure of success is really good. What do you tell the first K people as you interview them? Do you tell them that they have no chance? No, you open yourself up to a lawsuit. But what you do is you are willing to spend some time gaining information to then make a good decision later. But it does mean you miss out on some opportunities. And it does mean that certain candidates will have absolutely no chance if you use this process. Okay? Any questions about this? Yes?
Where'd the 1 over minus 1 go when you went from there to there?
Say that again?
So there's a 1 over minus 1.
Oh,
That's the issue.
yes.
Where did the minus 1 go?
I basically, you're right. I basically just was lazy and I shifted things. I should really, because I have m goes from k plus 1. So good question. So I have m goes from k plus 1 to m. I should really view this as it is a sum m goes from k to n minus 1 of 1 over m. And then when I view that, I'll get that this is approximately the log of n minus 1 minus the log of k. And I'm basically just saying the log of n is the same as log of n minus 1. So thank you. And remember to email me for that. It is a slight error there, but a very insignificant error. So you can get over 36% of the time the best candidate like this. Okay. Any questions on this? Yes?
So for your student who's actually trying to do this?
Yes, my student who is still single and has been single for many, many years. Yes.
Did he set a fixed ad?
It's a very good question. There were many things I tried to talk to him about. He's studying economics now. I think he had some rough idea of what n was. I'm not sure if his n was a reasonable number. He is at least a Williams student who's going to a strong Ivy League school for graduate study, so but hopefully makes him somewhat, well, anyways. Again, I do not urge you to do this. And again, if you are applying for jobs and you are not getting jobs, contact me. I often have contacts with companies and have helped many students find employment and just find opportunities that they might not have thought of. So, again, even if you're not a senior right now, if you want to do some advanced work and think about what you might want to do, always happy to chat. And the more I know about you and your interests, the more likely it is that I can match you up with something. Okay. Any other questions on the marriage secretary problem? Okay. So the number 1 over e occurs many, many times. We've already seen it once this semester. Anybody? Yes?
With better assumptions, how high could you get that number?
What do you mean by better assumptions? You mean more realistic assumptions?
Sure.
So with the realistic assumptions, does this allow you to go back to candidates? So as soon as you do that, then you have a much better chance if they are not taken. Then the question is always, if they're taken, can you give them enough money that they're willing to break a contract and come back? Yep. For certain amounts of money, people will do it. There are people who've accepted academic jobs and then have changed their mind. And sometimes it's very different if this has happened before you've signed the contract and you've only given a verbal agreement, but have not signed the following documents. There have been people who have broken contracts. What do you think happens to them?
They pay like a fee.
No?
They just never have a shot at the company again.
They never have a shot at that school again, and in fact, the knowledge spreads throughout all of academia. So-and-so did not honor their agreement. Be very careful if you give so-and-so an offer. They better really like where they're going. Now, I actually know somebody who did this, but there was more to the story. And so if you knew what was really going on, then it really wasn't bad. There are other people who they got a better offer, an offer that fit them better. And a lot of times you can just talk to people and say, look, I'm married, we have 17 kids, my spouse just got a job in this city that has a job for me as well. It would be so much nicer if we could be together than separated by 3 continents. And in situations like this, schools will often say, we understand, sure. But to just break the contract is often very bad. Somebody here might know about, I think it was Oil Can Boyd used to pitch for the Red Sox and was signed by the Toronto Blue Jays. And he had something in his contract that said if you start so many games, you get a certain bonus. When it was clear that the Toronto Blue Jays were not making the playoffs, they stopped starting him to make sure he wouldn't get the bonus and they wouldn't have to pay him a few $100,000. It worked. They saved a few $100,000. What do you think also happened?
He left the next season.
Well, no, I mean, as long as he's on contract, he's going to stay with them. What do you think this does to the Toronto Blue Jays? How is this going to hurt the Blue Jays?
Or is there like negotiations for players?
Right. Come to us. Look, we'll give you this wonderful incentive if you do these things. Yeah, I've seen how you honor incentives. And it makes it much harder. So a lot of times when you're doing these strategies, and I'm quite happy to spend some of class time thinking about this, are you short-term or long-term? Are you doing something repeatedly or doing something just once? If you're doing something just once, can you afford to screw people? Often, yes. If you are doing a repeated situation where you are a player in the market many, many times and your reputation matters. How many people have used Amazon? How many people have actually filled out any of those customer surveys? Not often. I usually don't do. Oh, I'm sorry. I'm very good at filling out those surveys. If you have a really bad experience, are you more likely to fill out the survey? And if you are looking at products, how many of you look at how many stars something gets and look at the comments? And if you see a lot of very negative comments, doesn't work when warmed. Lasts 2 days before breaks. If you see stuff like this, you are less likely to buy the product. So a lot of times if you're in a tourist situation, you might not have repeated customers. So you might be able to get away with some things. Maybe word of mouth is not going to hurt you. But now everything is spread so quickly that if you have a bad reputation, there will be serious consequences. So this is a situation where you're only playing the game once. What if you have multiple jobs? And then what if people notice, nobody in the first K people is ever hired by this company. Where am I in the hiring process? As an aside, for a lot of you, when you have job interviews, how many of you have had multiple job interviews with different companies? How many of you have done a practice interview before you have your first interview? If you haven't, do so. I am happy to be an interviewer for you and do a practice mock interview. I can be a company. That's not a problem. You do not want your first interview to be at the place you really care about. You want to have some practice interviews. You want to gain some experience. You want to gain some knowledge. Okay? So for what was going on over here, these are very unreasonable assumptions. You can start to make them better and better. And depending on what you define as a success, your strategy will start to change, and you can have a very high likelihood of getting somebody towards the top. And again, to me, some of the really interesting stuff is trying to quantify failure. I don't like having the second best person equally bad as ending up with the worst person. So what if you have some kind of lowered expectation strategy that at some point in life you choose to settle? And again, please don't ever use that phrase. You can use it theoretically, but in practice it doesn't work well. Okay? When would you want to settle? So this then becomes a very interesting question. Now, here's my first K. Here's my hope. And then here's my despair. Where is that critical threshold where you say, at this point, good enough? A lot of times you're going to get pressured. How many of you are seniors on the job market? You're the only senior on the job market? All right, I will just put these comments to you right now, but for those of you who are not seniors, this could be very useful later. You will get job offers that have time limits. Why do you think we're going to give this wonderful person a job offer with a time limit? Yes?
Because the offers that come in a month, they want you to give them an answer in 2 weeks. That way you don't have time to respond.
Okay, so I think you're close. I mean, wouldn't it be much nicer for him to allow him to hear from every place?
No, they don't want to do that.
They don't want to do that. Why don't they want to do that?
They want to force a response.
They want to force a response. So you're going to be in a situation where you will be forced to respond before you have all the information available. And you will have to decide, is this job good enough for me, or do I want to settle?
Kind of like early decision.
Kind of like early decision for colleges. What can you do if you have a dream company and you haven't heard from them, and you have a job offer that's going to expire in 2 weeks?
Wait till the last minute.
No, this is not rocket science. What do you do if you have a job offer?
Oh, I'll wait till the very end of the 2 weeks to see if I hear back from the company.
No.
You contact them.
You contact your dream job, right? If you have a job offer with a time limit of 2 weeks, don't wait till the last possible moment to contact your dream employer. Contact them and say, I would love to work for you. Unfortunately, I have this great offer that I have to let them know in 2 weeks. They're my second choice. They pale in comparison to you. I would love to avoid sleeping for you and work all those hours. Please let me know. Now, a lot of times you can do that, and the company will respond, and they will let you know.